Welcome to this video. In this example, I'm going to show you how to set up a linear static analysis in the Abaqus profile for HyperWorks. The first thing that we're going to do is make sure that we are in the correct solver interface. That will be Abaqus, and there's different options within Abaqus, but we're going to be in standard 3D, which is the default. Now we're going to open our model file, and we'll take a look at what's inside. We have this some kind of beam shape, the bracket, the bolt, and the cylinder. Now we're going to create our material. You can right-click, create material, or from materials driven. We are going to create steel material and give it some density. It's going to be an isotropic elastic material, so let's give it some Young modulus and Poisson's ratio. We are also gonna create 3 plastic data points with following values. Now we can review our material from the model browser. Now we're going to define the section properties, starting with the shell section. The material is gonna be steel. The thickness is gonna be 2, and we're gonna have 5 integration points. And we're gonna use the default section integration, which is Simpson. Second one, it's gonna be the solid section. And the material is gonna be steel. Now we're going to create a beam I section. And A, B, and C are going to be 12. And T1, T2, and T3 are gonna be 1. Now the third property, it's gonna be a beam section. With a steel material. And the beam I section that we just created. Finally, we are going to create our spring property with a steel material, 1 for DOF 1 and 2, and 0.1 for stiffness. Similarly, we are going to create another 2 spring properties for DOF 2 and DOF 3. And just a note here, grounded springs are typically used to stabilize a contact interface in case of rigid body motion prior to contact. That's why we are creating these springs. Now we're going to assign the property to the elements using the component browser. And we can also do this from the properties ribbon. Now we are going to create a new component for the spring elements. Now using the spring 0D ribbon, we are going to create spring 1 elements in DOF 1, 2, and 3 using the spring property that we just created. So we're going to select 3 nodes and assign the spring X property, create, and then we're going to do the same for Y and Z. And we're gonna do the same for the other side of the bolt. Now we're going to create a new component. It's gonna be called beams 1D for creating a beam element. We're going to assign the beam section property created before to this component. Now we're going to enable the panels view. And in the 1D panel, we're gonna go to the bars subpanel. And we're going to make sure the element types is set to B31 and the orientation to direction node. Now we select the node A and B and the direction node. We can review the beam axis and local system. And we can also change the visualization toolbar to 3D to see the 3D visual representation of the 1D beam. Now let's change the offset value to 6 to move the beam to be at the middle of the bottom plate of the tube. Now if you right-click in beam sections, you can see Hyper-Beam, and unlike HyperWorks 2022.2, Hyper-Beam GUI does not open when using the beam sections ribbon. Now we go to rigids because we're going to create kinematic coupling constraints. So we need to make sure copkin is select as element types. We're going to select multiple nodes and we're going to let Hypermesh calculate the independent node. The easier way to do it is select loops and we're going to select the loop. Now we change to nodes by path and we select our nodes. We click create and we're gonna do the same for the other one. Now we're gonna change to RVE3 to create distributed coupling constraint on the bracket. We wanna make sure element types is set to cope with this. And this is gonna be for the load application. Now let's start with the model setup, and we're going to create contact surfaces. But first, let's create our friction property, which is going to be a surface interaction, and it's going to have a 0.1 coefficient. Now we are ready to create our contact surfaces between the bracket, bolt, and tube, and the easiest way to do it is by using Create Auto Contact. We must select our three components, going to use the property that we just created, the friction. Now we're going to create the analytical rigid, but first we need to create a local coordinate system. So we go to geometry, and we first need to create a temporary node. Now we go to model, we click systems, and we select the center node that we just created. From the model browser, we can review the system, and we want the x coordinate to be in 0, 0, -1. And we change to y, y, z, and we change to 0, 1, 0. Now it's done. And we're going to assign the system. So we click the system, we select the center node, we make sure review select system is enabled, and also set displacement. Now it's gonna be under systems, transform, and we can turn it off. Now we go to interactions, analytical rigid, we name it A rigid, create, and we set the type to revolution, and we leave plain access as user defined. We pick the system that we just created. Now we hit start and we pick lines, and we're going to select these two lines. And we're going to update to create the analytical rigid. And now it's gonna be under boxes, and here we can change the color. Now we need to create the contact between the tube and the analytical rigid, but this time we're going to do it manually so you understand how to do it. We disable the analytical region and its component. And from the Solver browser, right-click, create contact definition, surface, and we're gonna give it a name, tube secondary. And let's select the elements that we want. And the easiest way to do it is by path. We need to create the contact pair. So right-click, create contact definitions, interfaces contact pair, and let's give it a name, rigid. And we need to select our entities, the A rigid and the tube secondary that we just created. We're gonna select friction as property. I'm going to adjust 0.2 and make the type surface to surface. We can do the same adjustments for our other contact pairs. Now let's turn on our analytical rigid geometry so we can review our contacts. Now we're going to create the bolt pretension, so we need to hide everything but the bolt. Now we're going to select some elements and hide them, because we are going to create a new surface for our bolt pretension. We select this facet by face and we give it a name bolt section. We change the load type to C load and the load magnitude, and we enable fixed bolt pretension. Now we're going to rename the automatically created load collector, one as pretension load and the other one as pretension fixed. Now we're going to change the direction of our force and we show all the elements. And actually our load should be in 100 direction, so let's change it, and now it's correct. Now we're going to start with the analysis setup, so let's create a load step. It's gonna be named pretension. And we're going to select the pretension load created before. And we need to create another one called SPC rigid. Now we are going to create a constraint on the center node of the analytical rigid. So let's go to Analyze Constraints. This is going to be a weighted constraint. And we need to create a node set. Let's name it rigid. And we're going to select the center node. We are going to apply an enforced displacement of 5 in DOF1 and close it. Now let's see our constraints. Because we are going to apply a fixed constraint on the pretension node, so let's change it to non-weighted constraint. And let's change to fix in DOF1. Now let's go back to our load collector and we are going to create a groups. Let's name it controls 1 and the card image is controls. We change it to parameters, time incremation, and we give it a value of 10. Now let's also create the output block. Let's just name it output. We select output, we enable frequency and we give it a value of 1. We select node output, and we type u.rf. We also select element output, position, and we want integration points. And for element output data line, we type max. Now from here, we are going to select step parameters. We're going to give it an increment of 500. We enable NIGEOM. The analysis is going to be static. We select data line, initial increment 0.01, total period 1, and maximum increment 0.2. Now we're going to create another load step, named load. And we're going to select the load collector pretension fix. We are also going to create another load collector named load. Now we're going to create a load on the RVE3 node. So we need to create a node set, and let's name it load. And let's select the center node. Finally, we give it a magnitude of 5000 and a direction of 0, 0, -1. Now we select the output that we created before, controls 1. We select step parameters and we give it an increment of 500. We select NIGEOM. The analysis is going to be static. We select data line, initial increment 0.01, total period 1, and maximum increment 0.2. Finally, we're going to create a load collector with card image initial condition. It's going to be named SPC tube end. And we're going to create a constraint, and we're going to create a new node set for the end of the tube away of the analytical rigid. So we select our nodes by path. And we select all DOF. And now we are done with the analysis setup.